Hello, everybody. Welcome to this audio precision webinar. Today we'll be discussing MEMS microphone test with the new APx517B. Daniel Knighten will be leading the conversation and providing demonstrations in APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items. First, please note that this session is being recorded, and the recording of the session will be shared with you next week. So be looking for an email from me with a link to watch this at your convenience. If you want to go back and rewatch, you'll have the ability to do that. Also, we are accepting questions throughout the webinar. You'll see a chat icon on your screen. Go ahead and submit your questions as you have them, and we'll periodically pause to answer those as needed, and we'll also stop at the end as well, and you can ask questions at that time if you prefer. So Dan has a lot to share with you today, so without further ado, Dan, I turn it over to you.
All right, thank you very much, Paige, and good morning, good evening, or good afternoon to everybody, depending which time zone you may be joining us from. What I'd like to go over in the next hour is just a practical application of our audio analyzer for measuring microphones. And I think, in fact, most of what I will talk about really applies to any microphone you may want to measure. But in today's session, we'll focus specifically on an array of MEMS microphones that have a PDM or pulse density modulation output. And we'll be doing it with an APx517 acoustic audio analyzer. In the first part of this presentation, I'll go over a little bit of the practical side of the physical setup, the analyzer we're using, and some other bits and pieces and choices we've made. And then really I'll just dive right into the software, and I'll show you the configuration of the software for this test and making some different measurements. And we'll make those measurements live here and now. And as Paige mentioned, as I go along, I'll try and address any questions that you might have. Feel free to submit them, and we'll also reserve some time at the end to address your questions. Okay, so first let's talk about the APx517. As I mentioned, almost everything, if not actually everything I'll show you today, can be applied to any of AP's audio analyzers. The reason we're demonstrating a 517 is that this analyzer is specifically optimized in terms of its physical inputs and outputs for the kinds of measurements where you have acoustic signals. In today's exercise, what we'll be specifically taking advantage of is that to measure a microphone, you need a sound source, you need a speaker. And one of the things that's very convenient about the 517 is it has a built-in power amplifier and can directly drive the speaker we use to measure our microphone with. The other thing we'll be taking advantage of is we need to get a signal back from a reference microphone, a measurement microphone, and we'll be using a unbalanced measurement microphone that requires constant current power. So we'll be taking advantage of the fact that that is also built into the 517. And finally, though, in this picture, the 517 that's depicted has a Bluetooth module for its input. What we'll be taking advantage of today is that you have your choice of many different digital input and output modules on the 517, and we'll be using a PDM16 module, which will allow us to simultaneously measure 16 digital microphones. Now, one thing you may be aware of is Audio Precision actually has two different PDM modules available. We have our original PDM module, just PDM, and then we have a newer module, PDM16, which we introduced a little more than a year ago. And these modules exist in parallel. You can purchase one or the other because they do have some different capabilities. Sort of the obvious or top level thing is our PDM module has a single data line, which will let you look at 2 microphones simultaneously. Our PDM16 module has 8 data lines, which will let you look at up to 16 channels simultaneously. The other is that our PDM16 module utilizes a remote pod. This lets you essentially physically move, if you will, the front panel of the instrument up to 10 meters away from the analyzer. So this is quite useful if you're doing your tests inside of an anechoic chamber. You can keep the analyzer outside of your chamber and just have the small and acoustically silent remote interface pod in your chamber. There is an option for a line driver for the PDM module, but that's not the same as the remote pod. The line driver tries to assist the PDM microphone in driving a longer cable, but you can still run into issues with reflection and signal attenuation with the PDM module and the line driver, whereas with PDM, this is a completely separate digital protocol between the module and the remote pod that completely isolates the effects of the long cable. So in today's example, we'll be using PDM16. You might use a PDM module, you might use analog, you might use I2S. It depends on the specific electrical interface of the microphone you're using. But just to move forward, we'll be looking at an array of 16 PDM microphones. So that's why we've selected this specific module. The next thing I want to touch upon is what is the physical environment in which we're going to test our microphones. So leftmost side of the screen, the ideal solution is to have an anechoic chamber, a room that has no acoustic reflections and is therefore a free field for testing purposes. Many of us don't have access or ready access to an anechoic chamber and have to make do. Another common solution is a test box. For all practical purposes, a test box is an anechoic chamber. It's just a small anechoic chamber. And the size of the chamber is directly related to the lowest frequency you can measure. That is to say, a chamber of any given size does eventually become reflective to sound, but the bigger the chamber, the lower that frequency is. For sort of a casual thought, if you wanted to have an anechoic chamber that was anechoic to 20 hertz, you'd need something that was on the order of at least 10 meters in size, so quite large. The test box, particularly the test box pictured, is anechoic, but not until you get to frequencies above 200 hertz. If your test requirements don't require that you measure below 200 hertz or 400 hertz, depending on your test box, you might find that a perfectly good solution. Now, I'm actually going to take an even completely different approach, as much out of expediency for what's available to me as anything else, which is I actually have my microphone under test, my reference microphone, and my speaker that will be generating the test signal, all sitting on the same surface. This is a reflective surface. It's in fact a tabletop, and I'll call this my half space test configuration. What's going to happen here is you will get a reflection off the surface, but because everything is sitting on that surface, that reflection is coincident or simultaneous with our test signal and just expresses itself as a doubling of the effective sound pressure level from my source speaker. which is actually, in the case of measuring a microphone, quite convenient. Next, let's talk a little bit about our choices for source speakers. I'll start on the left again with using a mouse simulator. In a lot of measurement microphone applications, we want to test systems for voice band signals, which is, approximately a few hundred hertz, maybe as low as 200 hertz, to maybe 8 or 10 kilohertz. And moreover, for many voice applications, there might be specific international standards that require us to use a mouth simulator, which simulates the acoustic properties of a human mouth. So in that case, we can supply a GRASS 44AA or AB mouth simulator. Now, in other situations, depending primarily on the frequency range you're required to test over, and also the sound pressure level you need to test over, that might pull you towards using, say, a professional studio monitor, something that has good extension over a wide frequency range, and which, moreover, could potentially be equalized to have a flat frequency response at a given reference location. And then finally, it turns out, and I'll demonstrate this to you today, that in many situations we can just use a relatively simple off-the-shelf speaker. In this case, I have a small little 3-inch single driver speaker that we'll use for our tests, and works quite effectively as long as I don't need either excessively high sound pressure levels or to go to very low frequencies. And then finally, sort of last critical piece of the puzzle is our reference microphone. So as I'll demonstrate to you today, I'm using a test technique I like to think of as simultaneous microphone substitution. And what I mean by this is I actually have a measurement microphone positioned very closely to the microphones under test. And I'm using this measurement microphone as a reference by which I can measure the other microphones. And when I'm doing this technique, there are a few things that come up. Probably the most common measurement microphone in the world is a 1/2-inch free field microphone. And it certainly has many desirable characteristics. It certainly has a flat frequency response above 20 kilohertz. But particularly when we're interested in microphone arrays, that probably indicates that we're interested in the phase response of the microphone. And if we're going to refer to our measurement microphone, then we run into the issue that while a 1/2-inch microphone may have a flat magnitude response beyond 20 kilohertz, it does not have a flat phase response. So if I switch to a 1/4-inch microphone, and even better, a 1/4-inch pressure field microphone, the phase response of the microphone is flatter to a much higher frequency. In addition, the 1/4-inch microphone is physically quite a bit smaller than the 1/2-inch microphone, and that means I can place it closer to the microphones I'm measuring without having the reference microphone actually disrupt the sound field around the microphones I'm measuring. So putting it all together, here's a depiction of what my physical setup looks like. I have my 517. It's directly driving a off-the-shelf speaker that I'll use for my signal source. I have my 1/4-inch pressure field microphone plugged into the front panel BNC. Now in my application, I actually have the pressure field microphone is placed 90 degrees to the sound field, and that's to take advantage of the fact that a pressure field microphone is has a flat frequency response in a free field when it is 90 degrees to the field. And then finally, I've got my 16 microphone array on an eval board that's connected to my remote pod, my remote interface pod, and then that is connected to the PDM16 input on the 517. So I do have one question's been submitted. Are any of these preconditions exclusive to MEMS microphone measurements? For example, could you use a 3-inch driver for a large diaphragm condenser microphone? So none of these preconditions are actually exclusive to MEMS microphone measurements. The things that particularly the question of what source speaker I would use, and I'll talk about that some more when we get to the hands-on of it, but the preconditions in my mind are the frequency range over which you need to measure your microphone and the sound pressure level at which you want to be able to measure your microphone. So the little speaker I'm using, while quite good, isn't very useful below about 200 hertz. And probably I can't drive it to more than about 114 dBSPL near field. So what speaker I would choose to use if I was measuring another microphone? Well, if it's a musical microphone and I want to say measure it all the way down to 20 hertz, say, I might need a different speaker, just something that has much better low frequency extension. And the same with the sound pressure level issue. For example, some microphones don't have an overlord point until above 120 dBSPL, or maybe 140 dBSPL, depending on the microphone. So there you would have to, make that selection again. And finally, the selection of the reference microphone I would use, that is very similar, actually, kinds of questions. But in this particular case, I would say that the main downside for microphone measurement purposes of a 1/4-inch microphone is its self-noise and its sensitivity, which are not going to be optimal for if I want to establish the ambient noise environment, or measuring distortion on a microphone, some additional questions. But the fact that it's small and doesn't interfere with the sound field as much is very handy, regardless of the type of microphone I'm measuring. And just to confirm, I am going to be testing 16 microphones today, and I'll talk a little bit. So my so-called half space measurement or tabletop demonstration, it definitely has some limitations as to what measurements you can make. But actually, we'll basically look at 3 fundamental measurements today: sensitivity, frequency response, and phase response. And for those 3, it actually works quite well, and I'll just show you right now. So first things first, I'm in APX software, APx517.0.1, and this is with a 517, and I'm starting out in signal path setup. This is exactly the view you get when you start the software. And I'll just go top to bottom. My output is going to be power amplifier because I'm driving a speaker. The 517 has 2 output connectors that I can switch between, and this is just sort of a convenience. So you can test, you could potentially timeshare 517 between 2 test jigs. Today I've got that output connected to output A. I'm going to use this in acoustic mode so I can set my output level in units of dBSPL. And Finally, on the input side, I'm going to use my microphone input for one of my inputs. I only have one measurement microphone, so I'll set that. It's on the unbalanced or BNC input. And it does need CCP power, and I'll turn that on. Now, like many of you, I am actually working from home and remotely controlling a system in our office. So unfortunately, I can't put an actual physical acoustic calibrator on the microphone to calibrate it. But instead, what I can do is I can select Calibrate from TEDS. Oh, sorry, let me set the acoustic mode first. And I can read the TEDS data electronically from the microphone. So this is the last, I'll say, factory calibration that was performed on this microphone. And I'll just use that and set the sensitivity from that. And then a little additional step I'll take is I'll set my input bandwidth to 22 kilohertz or 48K sample rate. And that's just because I don't plan to make measurements above 20 kilohertz. So I don't want to waste time processing data that I'm not using. Then I'll go ahead and expand verify connections, and I'll just turn on the signal generator and verify that I have a signal. And if I expand the FFT spectrum monitor, I can see that I've got a signal present. Now you'll notice it's not at the signal level I've set, and this is because I haven't calibrated my speaker yet. I'll go ahead and now go to references, and I want to go to acoustic output reference, and I want to set my acoustic output level. So now I'm going to set the system and say, hey, I want to find 94 dBSPL at the output. And it's somewhere, and I'll say it's somewhere between a millivolt and 2 volts of output. And let's just find that automatically. No, I wasn't able to achieve the target level in that range, so I might need to go to a higher voltage. I think that perhaps my setup is not quite right in my remote environment, but that is actually an opportunity for me to show you a different way I can do this. So normally I would have calibrated this so I get 94 dBSPL of output, so I can then make all my measurements relative to that. But I suspect somebody has moved a microphone or speaker in my test lab. And so instead, I'm going to make my measurements relative to my measurement mic. Let's go ahead. I can actually uncheck this if I want now, and I'll just set my generator in volts. So this is generating 1 volt at the speaker output. And what I'll do is I'll go ahead and go into input 2. And now I'll enable my PDM16 input. I'm going to turn on its clock output, and I'll turn on the VDD. And now if I open my input signal monitors, you can see I have one that's monitoring the analog reference microphone. and another that's monitoring all 16 MEMS microphones. And what I can do now is I'll add a primary result, and let's just add RMS level for the PDM16 input. And now if I want, I'll right click on my measurement mic RMS output, and I'll add a derived result. Sensitivity. And I'll say the comparison data will be PDM16. And that starts out with just one channel. I can add the others. I won't belabor it, so I'll just start out with 3. Oh, wrong button. And let's put this in dBFS per Pascal. And now if I want, what you'll notice is that this ratio, which is the sensitivity of the PDM microphone, so its output in dBFS for a given sound pressure level, is now actually independent of my stimulus signal. And this is the primary advantage of my use of an analog reference microphone in this simultaneous test, where I'm looking at the signal both from the analog reference microphone and the PDM microphones simultaneously. So now to expand this a little bit, let's go ahead and add a measurement. And I'll add acoustic response. And just for fun, let's sweep this full bandwidth. So from 20 hertz to 20 kilohertz, let's sweep this at 2 volts for 2.5 seconds. And let's just go ahead and run this measurement. Okay, now I have the impulse response of my analog reference microphone. I have the 16 impulse responses of the PDM microphones, the energy time curves, if I'm curious. And now here we're looking at the frequency response of the source speaker as measured by the reference measurement microphone. And here we have the same thing, but as measured by the MEMS microphones. Now I have a couple things I could do here. This includes, this doesn't tell me the frequency response of the MEMS microphones, and it really doesn't tell me the frequency response of the speaker either, right? This is the combination of the two. This does tell me the frequency response of the speaker because this is measured using a reference microphone, something that has a known flat frequency response. Now, if I wanted to, I could do a couple things here. I can do the same trick I did before. I'll add a derived result, sensitivity, and now we have, this is the actual frequency response of the MEMS microphone relative to the reference point of the analog measurement microphone. And I could, of course, add the additional channels. And again, I get them directly. Now, the other thing I could do here is I could equalize the speaker. And in fact, you can combine the two approaches. It's a little bit of a belts and suspenders approach. I'll go to my relative level result. And let's export this data. I just want the relative level of my mic. And I'll take all points. I'm sorry. And now I'll go to the EQ function in my measurement settings. I'll select the relative EQ. I'll import. And let's invert that since the result we want is a flat response. Now this speaker has essentially no energy output at low frequency, so trying to equalize that to flat won't succeed, but I'll go ahead and try and equalize it above 200 Hertz. Let's see what that looks like. Nope. So yeah, we're unable to do that. So actually, this is a real situation that happens from time to time. You can't, we make measurement microphones, but there isn't anything called a measurement speaker. And the big advantage of using a reference microphone is we can still get our result, and it subtracts or eliminates the speaker from the equation. Quite literally, it's simply divided out. Now, the other results we get here is the delay. And here's the delay of our 16 MEMS microphones. And then we can also look at the phase. Now that's acoustic response. The other measurement that can be quite useful is to look at the transfer function. So transfer function is something like a complex simple measurement. What's great about transfer function is it basically just calculates the frequency and phase difference between any two signals. And the application here is that we can make a measurement, we can find the frequency response and phase response, and therefore the sensitivity of a microphone, but using any signal we want. In this case, the greatest advantage is that we can use a non-sine wave based signal. So a common application of microphones is, of course, in voice applications. And in any kind of voice application, let's say a smart speaker or mobile handset, there's a good chance that there's an active signal processing algorithm that's eliminating non-voice signals. It's eliminating things like sine waves. So the advantage of transfer function is we can really use any test signal. The only thing we have to be sensitive to is the test signal has to have energy in the region of interest. So let's go ahead and make this measurement. And I'm going to do this using actual speech. And let's go ahead and the reference, so the question here is what are we calculating the transfer function between? And I'm going to go ahead and calculate it. Let's first do this with reference to the measurement microphone. Now match doesn't apply in this case. Match is useful if I'm making a measurement on a device in what I'd call an open loop configuration. So in this case, we don't have an open loop configuration. We're generating a test signal and measuring it immediately. So I'm going to go ahead and set match to none. And then time alignment refers to whether I want to take the captured signals and remove any time of flight to time align them with the reference. Since I actually do want to look at the phase, I'll say none. And then calculation mode, just leave that alone. FFT length, I'm going to set this to 48K, so I get 1 second resolution. And let's do, I want to acquire the totality of this signal. It's 10 seconds long, so I want to use all of it. And since the signal is human speech, it's an irregular signal, I'm going to do averaging to capture any transients in the signal. Okay, so let's go ahead and do this. Oh, we changed our analog input range. So let me go ahead and go into advanced settings and fix the analog input range. Okay. And now that I have done that, I realize this looks a little noisy because I'm looking at 16 results with some quite high resolution. But here is our frequency response. And because it's relative to that analog reference microphone, it's dBFS per Pascal. So we're looking at the digital audio signal coming out of the MEMS microphones in relationship to 1 Pascal of sound pressure. Here's the phase response. And again, this is relative to the reference measurement microphone. But the next thing that I look at, and I actually sometimes look at this right from the get-go, is the coherence. And one issue with a speech signal is it doesn't have very much low frequency energy, and it doesn't have much energy above 10 kilohertz. Our region where we're getting a good measurement is right in the middle here, where we have good coherence. Now, another interesting thing we can do, particularly when we're looking at a MEMS microphone and an array of them, is let's look at the phase relative to one of the microphones. So now I'll set my reference to one of those microphones. And let's run the measurement again. And so here we have the phase of the microphones in the array relative to microphone number 1 in the array. Okay. So that's a very quick overview of making some measurements on a MEMS microphone array with an APx517 and our PDM16 input module. I'd be happy to entertain any questions anybody might have at this time.
Awesome, thanks, Dan. While we wait for any questions to be submitted, I'll take a moment to remind everybody that AP does have a blog. You can go to www.ap.com/blog, and we do post regular content about all things audio test and measurement. Daniel himself is often a contributor and will be writing a post based on this webinar as well. So be sure to check out our blog in a couple weeks if you want to learn more about MEMS mic testing with the APx517B. And Daniel, it looks like we have a question.
Okay, let's address that question. So the question is actually a very practical one. So my MEMS microphones are already integrated into a device that has an enclosure. Think of a cell phone. Are there any techniques for measuring how well sealed the sound channel is within the mechanical enclosure? There's a rubber seal between the hole in the enclosure and the entrance of the component. Yeah, that's actually a test I've had to do on a production line many times. We call it a mic seal test. You might call it the same thing. So let's just go back and look at frequency response. And actually in this context, it doesn't matter too much if you're looking at the absolute or the relative frequency response or anything like that. So if we have a microphone and it has some kind of cavity, and that cavity needs to be sealed from the rest of the device, or is typically sealed from the rest of the device, if that seal fails, effectively the cavity size will change, and the cavity is the volume of the cavity will give you a resonant frequency, and you'll have a peak in your frequency response corresponding to that. So typically the way a mic seal test is done, or the most common way that I'm familiar with, is you measure the frequency response of your mic, and then you occlude or cover the port for the microphone. And if the seal, if the cavity is well sealed from the rest of the device, well, that occluded port should cause the frequency response to be severely attenuated. Maybe down to, 0 or near 0. And so from a test perspective, you sweep the device, make one frequency response measurement, then you occlude the port make a second frequency response measurement, and then very often you'll express the result as the ratio of the two, and you'll expect, you'll have a pass-fail limit that describes the attenuation with the port occluded. And essentially, if something busts through that limit line, you'll have a failure of the seal somewhere in your device. Are there any other questions at this time?
Looks like we don't have anything right now, but if any of you who are attending have any questions that come up down the road, feel free to reach out to us. We have a great tech support team. techsupport@ap.com can help out, and also feel free to reach out to your local representative as well. So with that, Dan, I think we can go ahead and wrap this up. Thanks everybody for attending, and I hope you have a great day or evening wherever you're at.
Okay, well, thank you very much, Paige, and thank you everyone who was able to attend. We will have more of these in the future.
Great. Take care, everybody. Bye-bye.